Hello and welcome to your second online summer pre-calculus class. I'm once again Mr. Marquez, and as always I will be your facilitator throughout this process. So today we're going to talk about real numbers, interval sets, how we graph them, how we can explain them, and I'm actually going to give a couple of examples real quick here. We're also going to talk a little bit about evaluating absolute values and find the distances between points. Now, to understand this, we have to go and draw a number line so you have an idea of what I'm trying to say. So, so far, we're only talking about the horizontal number line, and we know that a number line has all the numbers to the right are positive, and all the numbers to the left are negative. So I'm going to go ahead and kind of draw my number line here, and I'm going to draw from 1 to 8 just for illustrative purposes. But we do know that numbers are infinite, whether it be from positive infinity or all the way down to negative infinity, okay? So, and I'm going to leave it there, but so on and so forth, okay? So what we're going to talk about is when we have an answer, and maybe we're going to see this a little bit later on when we talk about inequalities, but when we have an answer, a possible or possible answers, they're always going to be found in the number line, at some point in the number line, okay? So there are rules for talking about our graphing and intervals, and we have, for example, like we have here, we have brackets and we have parentheses, and we have a whole system of, we can call it nomenclature, or we can call it terminology, or we can call it symbols to illustrate how intervals in real numbers work. Now I'm going to talk a little bit about this real quick, and you can follow in your textbook. This is section 1.1 of your textbooks, and we're going to look at these symbols right here: union, intersection, and no interest, or not present, excuse me. Let me write this a little better. Not present. So guys, as I finish each example, what I'm going to do is I'm going to erase so that we have more space on the board and can illustrate them better. Right now we're working with this. Now we use the letters S, V, and T, and what the letters represent are basically sets of numbers. So for example, set S includes numbers 1 through 5. Set T includes numbers 4 through 7, and set V includes numbers 6 through 8. Now we have three symbols: union, intersection, and not present. When we talk about a union, we talk about possible numbers that are present in S, or that are present in one set and they're present in another. Which kind of brings us to our example, because in this example they want us to find the sets of S union T, S intersection in T, and S intersection in V. And we're going to see what numbers are present. So I'm going to step out of camera just to make sure that everything is going smoothly and that we have no issues, no technical issues. All right? And let's look at this. So I know that all of my sets in S are 1 through 5, and all of my sets in T are 4 through 6. So if I'm looking, and then for S union T, I want to know what numbers are present in S, what numbers are present in T, and if they're present in both sets of numbers. Sometimes they're not all going to be present in one set of numbers. Sometimes they're going to be present in some, and sometimes they're going to be present in another one. So what we do is we unite them. So what numbers are present in S? 1 through 4, and T 5 through 7. So union literally means that we're going to unite them. And we're going to say that the union of S and T includes numbers 1 through 4, and, well, actually, let me write it down here. I think I have more space down here, okay? So we're looking for S union T, and the numbers that are present there are 1 through 4 that are present in S, and then, or 1 through 5, excuse me, and then 6 and 7, which are present in T. Again, S union T. we're uniting them, we're putting them together, right? We're combining them if you want. So what numbers are present in S? Well, numbers 1 through 5, which is what I wrote here. And since T also has 4 and 5, that means I can unite them and add 6 and 7. Now, one condition that you have to understand is that the numbers that you unite have to be present in one or in both of them. So I know, so even though 1, 2, and 3 are not present in the T set, 4 and 5 are. So that's why I can unite them. So that's why I write 1 through 5, because 4 and 5 are also present here. And then I unite them with 6 and 7, and that's why it's called a union. Now, that may not be the technical term for it, but I use it because I think it's easier to explain. So again, a union of two sets of numbers, they have to be present in one or in both. So I know that the numbers present in the S set of numbers is 4 and 5, which are also present in T, and that's why I can unite them. So I write 1 through 5, and then 6 and 7. There you go. Now the next thing that we're being asked to find is, in this example, is the intersection of S and T. Now the intersection of S and T are the numbers that are only present in both S and T. Now the union, one of the numbers have to be present in S or in T, but in the intersection, they both have to be. It's a requirement, okay? And again, let me explain it. In the union, the same numbers have to be present in one set or in both sets. In this case, 4 and 5 are present in both sets, and that's why I can unite them. But that doesn't, it's not a requirement for the numbers to be present in both sets, okay? As long as there's one that I can unite, then that's good. But in the intersection, they both have to be present. So what numbers are present in both S and T? And if you're thinking 4 and 5, that is correct. The intersection is 4 and 5 because they're both present, okay? So in that case, you simply say 4 and 5. And since they're present, we write them in brackets. Although in your textbook, you'll find a different symbol. You know what? Let me see if I can write the symbol just similar to the one that you have in your book. I'm not the best illustrator, but if you have your book, you can follow along. It looks a little better. So in a nutshell, 4 and 5, the intersection of S and T are 4 and 5 because they're present in the S set of numbers and they're also present in the T set of numbers. So recapping real quick, okay? The union, in order for me to unite two sets of numbers, one of the number sets or more has to be present in 1 or 2. In other words, if I look at S and T, 4 and 5 are both present, so that means I can unite them. So that's why I write 1 through 5, and then I add the other two number sets that are in T, which are 6 and 7, and that's the union of S and T. Now the intersection is an entirely different story because they both have to be present. Well, 4 and 5 is present in S, and 4 and 5 is present in T, so the intersection is 4 and 5, and that's why I write it like that. Now the last one that they're asking me to find is the union, or not the union, the intersection of S and V. The intersection of S and V. Now, remember, the intersection, in order for an intersection between two interval sets to occur, the numbers must be present in both sets. So they have to have the same number. If I look at S, I have 1 through 5. If I look at V, I have 6 through 8. So none of the numbers are present. So in this case, we say that since they're not present, we simply use this symbol, which states that there is no intersection between S and V because the numbers are not present. I'm going to step out of camera, making sure that everything is still a go. All right. So recapping the example, this means union. And in order for me to unite two sets of numbers, one or more numbers has to be present in both sets. In this case, this is true. And that's why I wrote 1 through 5. And then since 4 and 5 are in T, I just unite them with 6 and 7. In an intersection, which is this one, that means that both numbers, the same numbers must be present in S and in T. If I look at S, I have 4 and 5. If I look at T, I also have 4 and 5. So that means that the numbers that allow the intersection to occur of 4 and 5. And finally, the intersection of S and V. Well, if I look at S and V, they don't have any numbers, or they don't share the same numbers, so that means that they're not present. And that's it for that example. It's really simple. It's kind of like a puzzle. You have to pay close attention in order to be able to put the pieces of the puzzle together. So I'm going to go ahead and I'm going to erase this, and then we're going to talk a little bit about the next example, okay? So I'm going to erase my number line, okay? I'm going to erase this, and then I'm just going to rewrite this example on the left side of the board. And in your textbook, it says example 5. Since this is a summer course, it's not a regular semester course, some examples will be skipped. Example involves understanding interval notation. Now this is before I start with interval notation, I want to review, because in 7th and 8th grade, when they talk about inequalities, they'll talk about these symbols. And this symbol means less than, and this symbol means greater than, and when they have the little lines made, it means less than or equal to, or greater than or equal to. And just to kind of review a little bit, for example, if you had an inequality where your answer says x is greater than 3, and that would mean that when you graphed it, that meant that x was going to be any number greater than 3, or from 3 to positive infinity, right? And you used to kind of like draw a graph of a line going from 3 to infinity. So a lot of people still get confused with this, but you have to see this as reading a sentence. Now, you normally read a sentence from left to right, okay? So the same applies to this. If I look at this, it means that A is actually less than X because it has this symbol, and X is less than B because it also has this symbol. And what that means is that whatever number A would be is going to be smaller than X, and whatever number B would be is going to be greater than X. Because we're seeing interval notation, so we're not seeing, we're seeing segments of a real number. And whenever you have these kind of pairs, we're going to assume that the first number is always going to be A, and your second number is always going to be B. And also that we're going from smaller numbers to larger numbers. So what we're going to do is first derive the notation, and then we're going to graph them. One thing that you want to understand also is that when you have a bracket, that means that X is part of the answer, or A, let's just say A to make it easier. That A is part of the answer, and it would be a shaded point on a graph. And if we have a parentheses, that means an open parentheses, that B is not part of the answer, and it would be an open point. Now let's get down to it. What does this mean? Now, if I look at the first example, by the way, this is example 5 on page 7 of your textbook. Like I was saying, some examples are going to be compressed because this is a summer course and we're trying to move a little bit faster. Anyway, so I want to first write the interval notation. And I know that this would be A and it's smaller. So I know that it's going to be either less than or equal to. Now, which one am I going to use? Well, if A is in a bracket, I'm going to use less than or equal to. So I'm going to start out with my small number, which is -1, because it's my smaller number of the two. And since it's in a bracket, instead of less than, I'm going to say less than or equal to X. And that's the first part of my interval notation. Now, if I look at 2, which is B, meaning going from a smaller number from a larger one, and B is in an open parentheses, that means I'm not going to use less than or equal to, but rather less than B. And I would graph that on a number line simply by saying, this is 0, that it's going to start at -1, and it's a closed point. It's a shaded point because -1 is in a bracket. And then it's going to go to somewhere between +2. But since +2 is in a parentheses, it's an open point, so it's not shaded. And all you do is you trace the line segment. And what that line segment is saying is that whatever number that my answer would be, whatever numbers are between -1, including -1, and 2 without including 2. So it could, just to give you an example, it could be any number from -1 to +1.99999, right? It just will never be 2. And the same thing is true for this one. So again, we're going to start with our interval notation. 1.5 is a smaller number, so I know that that's going to be there, 1.5. And 1.5 is in a bracket, so I'm going to use less than or equal to. x. And it's going to move from 1.5 to positive 4, from a smaller number to a larger one. And since 4 is also in a bracket, well, I say 1.5 is less than or equal to x, and x is less than or equal to positive 4. And that's my interval notation. Now, how do I graph that? Well, in this case, it's positive, so I'm going to just write from 0 to 4. And you're going to say any number between, and since they're both in brackets, that means that they're going to be shaded points. So 1.5 is between 1 and 2. And then 4, of course, is also in brackets. So that means that my answer or my number set should be somewhere between 1.5 and 4. Now I have negative 3 to positive infinity. Negative 3 to positive infinity. Now, positive infinity has no numbers. I can't say that positive infinity is, such number, or that negative infinity is such number. Hence, that's why they're both in brackets. So you would just say, you don't have to do two intersections because technically negative is A and B is infinity, and I don't know what infinity is, so I would just say that it would go from negative 3 is less than x. And less than because they're both in parentheses. Now you'll also see it in some Algebra 1 books expressed as x is greater than negative 3. They both mean the same. It's just the content in which you read the sentence, okay? So how do I graph that? Well, I know that they're both parentheses, so they're open points. So it would start at negative 3, and since I don't know what number positive infinity is, it's not going to be a line segment, but rather a ray, or in other words, it's just going to be an arrow that in this case extends infinitely to positive infinity. And that's example number 5. It's really simple. It's nothing out of the ordinary. It's really easy to do and use. So I'm going to go ahead and erase this. I'm going to step off camera just to make sure that everything is running smoothly and that I have no technical glitches. And I'm going to go ahead and erase this. And then go and talk about absolute value. So I'm going to go ahead and draw another number line. And I'm also going to erase this. And the other number line is here. And let's say you have negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. But we all know that that extends positively in, or extends infinitely in both directions. Let me just try. Those are horrible arrows, by the way, but use your imaginations. Okay, so an absolute value is just the distance between any number, whether it be on the left side or on the right side, to 0. So if I want to find how many times I have to move to get from negative 2 to positive 0, well, 1 and 2. And if I want to know how much I have to move to get to positive 2, from positive 2 to 0, 1 and 2. So that means that the absolute value is just the distance of any number on a number line to 0. Okay? That's why they always say that absolute values can't be negative, and it's because regardless of which direction you move, that number is going to be the same, whether you're moving from left to right or from right to left. So this is example number, I believe, 6 or 7, and it's on page 7, at the bottom of page 7 of your textbook. So what is the absolute value of 3? Since 3 is the distance of 3 to 0, if I wanted to go from 3 to 0, I would have to move 3 times, so we say that the absolute value of 3 is 3. The absolute value of 0 is 0 because, well, it's there and I'm not moving. The absolute value of negative 3. Now, this is what I was trying to explain. So negative 3 is here, so regardless if I'm moving in the negative side or in the positive side, the answer is still 3. So 1, 2, 3, which is why we say that the absolute value of negative 3 is 3. And finally, the absolute value of 3 minus pi. Now, this is a tricky one because a lot of people will look at this and say, well, the absolute value of 3 minus pi is 3 minus pi, but that's incorrect because pi is a slightly larger number than 3 because pi has an approximate value of 3.14. So 3.14 is technically larger than 3, so the absolute value of 3 minus pi is actually pi minus 3. Okay, and that's example number 7 on page 7, or page 8, excuse me. Very simple, nothing out of the ordinary. We've done it a million times. I'm going to go ahead and erase this, and I am going to go on to example number 8, which is on page 9 of your textbooks. Ladies and gentlemen, I'm going to leave a number line because I want to explain this point. Now, example number 8 is talking to us about the distance between points on a number line, and it gives us a formula that says b, the absolute value of b minus a. And the example says find the distance between two and negative 8. Now, the distance formula is used to find distance between one point to another. And the formula states that it's the absolute value of b minus 8, but in reality, since it's the absolute value, I can also use a minus b, and I would regardless get the same answer. So all I need to do is just plug in the numbers into my formula. If I want to find the distance between 2 and negative 8, I am going to assume that a equals 2 and b equals negative 8. So you're just going to plug in the numbers and say the distance of a to b equals the absolute value of b minus a. Again, you can use a minus b, and since you're calculating the absolute value of the answer, you're going to get the same number regardless, but I'm going to use the method that they do in your book so that we're all on the same page, literally. So b minus a would be negative 8 minus 2. And I know that from your integer rules, negative 8 minus 2 is negative 10. And you would say the distance of AB is the absolute value of negative 10. And the absolute value of negative 10 is 10. So we say that the absolute value, or that the distance between A and B, the distance of A and B in this case, equals 10. Okay, and that's it. That's the end of this section, ladies and gentlemen. After you've seen this video, you've rewinded and you've made sure that you understand all your work, you're going to go to page 11 and you're going to work on problems 41, 47, 67, and 75. So I'm not your favorite math teacher yet, but I'm pretty sure that by the end of the summer I will be. So stay safe and I'll see you guys soon.